Hello everyone, welcome to the first video lecture on the Safe in Cave Simulator. I am Hermínio Honorio, and the video I'm presenting today is the part B of our previous video in which I present some practical examples on tensors and tensor operations. In the last video, we saw some important concepts related to the internal product of basis vectors, internal product in general, or dot product, and especially the implications on the basis vectors. We also defined the nabla operator, and we also discussed the Einstein notation, which really simplifies the representation of any type of tensor. The important thing is that repeated indices imply summation. And we also saw the concept of tensor, rank 0 tensor, rank 1 tensor, and so on. Okay, now let's put all of this together and try to solve some practical examples. So in the first case, we want to know how to perform the internal product between two rank 1 tensors or two vectors. Of course, we all know how to do this, but let's use the Einstein notation for this, because Einstein notation allows us to solve this problem, which is a very simple one, but it also allows us to solve a very complicated problem with the same level of manipulation. Okay, so to solve this problem, I would write vector v like this and vector w like this. So vector v would be v sub I e hat sub I. Now we have the dot product here, and the vector w would be represented by w sub j and e hat sub j. The important thing here is that if I already used the index I cannot repeat the index I here. I have to use another letter. This is very important. I cannot use for one vector, if all the indices that I use to one tensor, I cannot repeat to the other tensor. I have to choose other letters. So that is why I'm using I and j here. Now, we have a dot product here. V sub I and W sub j are scalars, they are components, they are numbers. So I can collect all of those components to the left, like this, and leave the directions to the right. So here I have the internal product between e hat I and e hat j. We saw in the last lecture how to perform this operation. This is actually the Kronecker delta function, and this function tells us that this product will be 1 if I equals j, or it will be 0 if I is different than j. So every time I is different than j, this will be 0, or everything will be 0. Remember that this is a summation, right? This is the Einstein notation. So repeated indices imply summation. So we have I repeated here, vi e hat I, and we have j as repeated index. So we have a summation of I and over j. And every time we have I different than j, this term will be 0 and it will be vanished. So this whole term will vanish. And every time I equals j, this term will be 1. This implies that we just have to remove this term and make I equal j. So I just substitute the subindex I by j, or I substitute the subindex j by I. In this case, let's replace j by I, and we are left with this expression here. Why we don't have anything else here? Because this term is 1, I don't have to write 1 here. So the dot product between vectors v and w can be written using Einstein notation by v sub I, w sub I, which implies a summation of I from 1 to 3. Okay? Notice that there is no direction associated with this number. This is just a number. This is just a scalar, right? Vi is a scalar, Wi is a scalar. When we perform the summation, it will just be another scalar. So the result between the internal product, the result of the internal product between two rank 1 tensors is a rank 0 tensor. Okay? How can we verify this? We can perform the dot product the way we are used to. Actually, maybe not everyone, but everyone starts to learn like this. We can write vector v like this, using this representation, and vector w using this representation, and we perform the dot product between these two vectors. And this is done by performing the distributive multiplication, or distributive dot product here. By doing this, we get these terms. We get something, you can do it by yourself and verify that you're gonna get these results here. Here I painted in blue the dot product between the same vectors, and in red the dot product between different basis vectors, because we know that all the dot product between different vectors is 0, and the dot product between the same basis vectors is always 1. So from this result we get this expression here: v1 w1 plus v2 w2 plus v3 w3, which can be represented by this simple expression in Einstein notation. Okay, and this is just what we obtained here. You see the difference between the computation between the two approaches. In this case, I solved with 3 lines, just 3 lines, and in this case, I had to write a lot of things until I get to the solution. Okay. Now let's go to the next example, which is the internal product between a rank 2 tensor and a rank 1 tensor. Remember, rank 2 tensor is represented by uppercase, bold, Roman letter, and rank 1 tensor, lowercase, bold, Roman letter. The way we can solve this by using Einstein notation is by writing the rank 2 tensor A as I sub ij in the direction e hat I, e hat j. Okay. Dot product between with the vector v. In vector v, I can write v sub k, e hat sub k. Remember, I already used the letters I and j for tensor A. I cannot use I or j to represent vector v because it was already used. I have to choose another letter, in this case letter k. Okay, the next step is to collect all the components to the left and leave the basis vectors to the right, just to make it simpler. So I collect all the components to the left, I leave the vectors to the right, and we can see that we have internal product between e hat j and e hat k. This we know this can be replaced by the Kronecker delta function, and as you saw in the last example, this means that we can eliminate these two directions. We can just remove it and replace j by k, or replace k by j. Let's see what I've done here. Okay, in this case, I chose to replace k by j. Okay, if I had chosen to replace j by k, it would be a sub ik vk in the direction e hat I. It would be the same thing. Okay. So this is the result. So you can see that the result now, we have a scalar. This is a scalar. Of course, we have repeated indices here. We have j. So we have a summation over j. So but this will be a scalar associated to one direction, which means that the result of the internal product between a rank 2 tensor and a rank 1 tensor is also a rank 1 tensor. Okay, how can we expand this term? I can expand this term by choosing I equal 1 and performing a summation. So in the direction 1, I perform a summation of j from 1 to 3, and then I choose I equals 2, so in the direction of 2, the direction e hat 2, I perform the summation again of j from 1 to 3, and so on. So I would get something like this, in the direction 1, so I always have the first index here as 1, because this is I, the index I, which is equal to this one, and index j varies from 1 to 3, and then I go to index direction e hat 2, e hat 3, same thing. So this small expression here actually means this big expression here, and this is for a simple vector. Okay, now what about the internal product between rank 4 tensor and a rank 2 tensor? In this case, we can write this rank 4 tensor like this. We have 4 directions associated, so we have C sub I, j, k, l in the directions e hat I, e hat j, e hat k, e hat l. Dot product, I cannot use these letters anymore, I, j, k, l, I cannot use it anymore, so I just choose R and S. So A is a rank 2 tensor, so there is 2 directions associated. So I have R sub A sub RS in the direction E hat R, E hat S. Okay. Next step, we throw all the components to the left and leave the directions to the right, just to make it easier. Then we identify here a dot product or a contraction. It is very common to call this dot product between 2 basis vectors as a contraction. It is a contraction because these terms disappear. Those 2 directions, they disappear. So we call it a contraction, single contraction. We can have the double dot product that we're going to see later, and in that case we would say a double contraction. We're going to see it later, but this is a contraction. We know that this is the Kronecker delta between L and R, and this means that we can replace L by R or R by L, and we can remove this. In this case, we replaced L by R, so we had L here, but now we have R. We can see that we already have a summation here because R is repeated here. And yeah, this is the result. The result is a scalar, a component associated to 4 directions. What does it mean? It means that the internal product between a rank 4 and a rank 2 tensor is a rank 4 tensor. Okay? If you want to expand this yourself, to write this as a regular representation, yeah, feel free to do it yourself. I'm not gonna do it, okay, because it will take 81 components to perform this operation. Yeah, it's completely impractical. Now, in this example, I introduced the double dot product, which I just told you. You can also call it a double contraction. So in this example, I'm performing a double dot product between 2 rank 2 tensors, A and B. So we can write this like this. So tensor A, we write A sub ij, e hat I, e hat j, double dot product, B sub kl, e hat k, e hat l. Remember, I already used the sub-indices I and j. I cannot use them here anymore. I need to choose other letters, in this case k and l. Second step, throw all the components to the left, leave the directions to the right, and we are left with this. Now we have a double dot product. Okay, first thing to perform a double dot product. We see the double dot product here. I'm gonna call this term the first term to the right, and this one the second term to the right. And this term, E hat J, I'm gonna call it the first term to the left, and E hat I, I'm gonna call the second term to the left. To perform a double dot product, I must have at least two directions to the left and two directions to the right. Okay? I can have more directions here, and I can have more directions to the right. It doesn't matter. As long as we have two directions to the right, to the right, and two directions to the left, we can perform the double dot product. Okay? So this is the first term to the left, second term to the left, first term to the right, second term to the right. The way to do the double dot product is to perform the dot product between the second term to the left and first term to the right, which is this one, second term to the left with the first term to the right, so E hat I and E hat K, and a dot product between the first term to the left and second term to the right, so E hat J, E hat L. Okay, this is how we perform a double dot product. Every time you see a double dot product, you need to remember it is performed like this. Second term to the right, first term to the left, second term to the left, first term to the right, first term to the left, second term to the right. This is how we perform the double dot product. And from now on, we already know the drill. This is the Kronecker delta between I and K, which means I can replace K by I or I by K. And the Kronecker delta between J and L means that I can replace L by J or J by L. And if I do this, I get that the result of the double dot product between A and B, two rank 2 tensors, is just a scalar. So this is a scalar. We have repeated indices. I is a repeated index, J is a repeated index, so we have a summation of I from 1 to 3 and another summation of J from 1 to 3. This will be a big expression, but in the end we're gonna get a scalar. So the double dot product between two rank 2 tensors is just a scalar or a rank 0 tensor. Okay. Now, what about the double dot product between a rank 4 and a rank 2 tensor? It's the same thing. We just have to write the rank 4 tensor like this. See ijkl in the directions ijkl, double dot product. This is tensor A. I use different letters. I do not use ijkl again. I use rs. Second step, I throw every component to the left. I leave the directions to the right. And you can see that we have a double dot product. We have two directions to the left, to the right, and we have four directions to the left. So we are good. We only need two directions to the left to perform the double dot product. The double dot product is performed by doing the dot product between the second term to the left with the first term of the right, and the dot product between the first term to the left and second term to the right, which is this one. It means that K must be equal to R and L must be equal to S, so I can replace K by R or R by K and replace S by L or L by S. So I end up with something like this: C ijkl A sub KL. So I already have for every index pair ij, I have a summation over K and L, okay? So if I choose a value for I and a value for J, I have to perform summation for K from 1 to 3 and L from 1 to 3 for each. So this is a second order tensor or rank 2 tensor because this is a scalar associated to two directions. Therefore, the double dot product between a rank 4 and a rank 2 tensor is a rank 2 tensor. And this is exactly what we have for stress. Stress equals the stress tensor, which is a rank 2 tensor, equals the rank 4 tensor, the stiffness matrix, what we call the stiffness matrix. It's actually a rank 4 tensor, double dot product with the elastic strain. And elastic strain is also rank 2 tensor. Okay. Now let's do something involving the Nabla operator. In this case, let's consider the mass conservation equation for incompressible flow. The mass conservation for incompressible flow is just the divergence of velocity vector equals to 0. So the dot product between the Nabla operator and the velocity vector is 0. Actually, what we call a divergence is the dot product between the Nabla operator and a tensor. Not a rank 0 tensor, but any other tensor. It could be a rank 1 tensor, rank 2 tensor, rank 3 tensor, and so on. We cannot use the rank 0 because rank 0 there's no direction associated, so it doesn't make sense to perform a dot product between a vector and a scalar. It doesn't make sense. So how can we represent this operation, this equation using Einstein notation? Well, for this, we can represent the Nabla operator like this. Okay, so del sub I e hat I dot Vj e hat j. Remember, I already used subindex I here. I cannot repeat it here. Now, the second step, I throw all the components to the right, to the left, and leave the directions to the right. So I have the dot product between e hat I, e hat j, which means that I can substitute j by I or I by j, and the result is, so using Einstein notation, the divergence of the velocity vector can be written like this: del sub I v sub I, which implies summation over the subindex I, and if we do this, we get this result, this partial derivative of v1 with respect to x1 plus partial derivative of v2 with respect to x2, and so on. And this is equal to 0. Okay. This would be the mass conservation equation for incompressible flow using Einstein notation. What about this expression here? How can we use Einstein notation to represent the dot product between the Nabla operator and the Nabla operator applied to a scalar P, pressure P? That actually would be we can also call it the divergence of the gradient of P. We want to do it using Einstein notation, and we can do it by replacing the first Nabla operator by del sub I e hat I dot product del sub j. You see, I cannot use I again, I use j. We have the direction e hat j, and we have pressure here, or P, whatever P means. You see that P could be here. Actually, P should be between del and E, but I accidentally put it here. But it doesn't matter, this is not a mistake. As long as P is to the right of the derivative, we are good. Okay, because we're taking the derivative of p, so p has to be to the right. Okay, now the second step is to put every component to the left and leave the directions to the right. So, oh yeah, this is just a suggestion, right? In this case, I left p to the right, but it doesn't matter. The important thing is to recognize that the dot product is performed between e hat I and e hat j, which means that we can remove these directions and replace j by I or I by j. And if we do so, we end up with two derivatives over with respect to x sub I. So we can write this del I squared, and this means the Laplacian, right? If we perform this expansion, if we expand this, if we perform the summation, because you see this is a repeated index, right? This is a repeated index implies summation. So there is a summation of this index. And if you do this, we get this expression, and this expression is the Laplacian. So the result here is the definition of Laplacian. The conclusion is that the divergence of the gradient of a scalar equals the Laplacian of that scalar. Okay. Next example, the divergence of a rank 2 tensor, or the dot product between the nabla operator and the rank 2 tensor. Again, the nabla operator is given by this, del sub I e hat I, dot product, sigma jk. I don't use the index I anymore, I use jk. So sigma jk in the direction j and k. Now I throw everyone to the left, leave the directions to the right. I recognize the internal product between e hat I and e hat j. So I eliminate these directions and replace j. What do I do here? I replace j by I. So, okay, yes, I can replace j by I or I by j. In this case, this was j, I replace it by I, this first index of sigma. And this is the result. So for every direction e hat k, I had a summation of I from 1 to 3. So this is the result. So the result of this, the divergence of a rank 2 tensor is just a vector, a rank 1 tensor, because the component is associated to a single direction. And if we expand this, we can get these expressions here. So in the direction number 1, I have this expression, the direction number 2, direction number 3. This is a vector, right? Okay, now let's consider an example a bit more complicated. This is the Cauchy stress tensor for a Newtonian fluid. So this is the stress tensor, rank 2 tensor. This is pressure, P is pressure. I is the rank 2 identity tensor. Lambda and mu are the Lamé parameters. So lambda is the first viscosity. Mu is the dynamic viscosity. They're scalars, okay? This is the divergence of velocity vector. This is again the identity rank 2 tensor. This is the gradient of a vector, and this is a gradient of a vector v transposed. Okay, this is transposed. We want to know, okay, so the first thing we want to consider this stress for incompressible flow. So if we have incompressible flow, this term vanishes and we are left with this expression here. So this is the Cauchy stress tensor. We want to know how to compute the divergence of this stress tensor using Einstein notation. How can we simplify? Can we simplify this expression using Einstein notation? Okay, so let's analyze this equation term by term. So let's start from the first term. This is the divergence of pressure multiplied by identity rank 2 tensor. So let's use Einstein notation here. So this is the nabla operator, dot product, P, and this is the identity rank 2 tensor. So this is subindex I, subindex JK. I perform the contraction between E hat I and E hat J, which means that I substitute J by I. So now here I have I sub JK, and here I have big I sub IK. Okay, I replaced the J by I here. And I'm left with this term here. Okay, the thing about the identity tensor, identity rank 2 tensor, because it's a rank 2, we can think of it as a 3 by 3 matrix, and the identity tensor is just 1 in the diagonal and 0 in the off diagonal values. So every time I equals k, we have 1. Every time I is different than k, this number is 0. So this is identical to the Kronecker delta function. So what we can do here is just simply make I equals k and remove this term. This is what I just said. I sub ik is 0 if I is different than k, and I sub ik is 1 if I equals k. Therefore, we can simply remove this term just as if it was a Kronecker delta and replace k by I. Okay? So by the end, we have this expression here. And if you see that I is a repeated index, I can expand this from 1 to 3. Then I recognize that this is nothing else but the gradient of pressure. So the divergence of pressure multiplied by the rank 2 identity tensor is just equal to the gradient of pressure. Most of us already know this, but it's nice to have a tool that allows us to analyze this to reach the result analytically, right? This is an important result. Let's save it here in this square and move to the next component. We already solved a problem similar to this one before. I think it was example number 7. Yeah, this one. But now, now we have this viscosity here. But the problem is very similar. We just have this viscosity here. It's not completely similar because this V is not a scalar anymore, but it is a vector. Okay, so let's go through it. This is the nabla operator in dot product. Nabla operator again with different indices. Here we used I, now we have to use a different one, so J. And Vk E hat k is the vector V, right? Now suppose mu is constant, we can take it out of the derivative, so it goes to the left. We have a contraction between E hat I and E hat J, which means I equals J, and we are left with this expression here. We see del sub I, this is del sub I squared, so Laplacian, and this Vk E hat k is the vector V. So this is equal to the Laplacian of a vector. The Laplacian of a vector would be just the second derivative of each component of that vector. Okay, so it will also be a vector. Okay, so this is the result for this expression. The divergence of the gradient of something is just the Laplacian of something. Now let's move to the next term, which is pretty similar to the first one, but now we have the transpose here. Let's see how we handle the transpose. So we write this expression just as before, but now we have a parenthesis here, and we say that this is transpose. We have del sub j, e hat j, vk, e hat k. To perform the transpose, we can just swap some of those indices. For example, we can swap j and k from the directions here, or we can swap j and k from del and v. It doesn't matter. In this case, we chose to swap the indices of del and vj and v. So you see the directions e hat j stay the same, e hat k and e hat k stays the same, but del j becomes del k and vk becomes vj. Okay, this is how we perform the transpose. Now let's do the same drill as before. We perform the contraction between e hat I and e hat j, and we end up with this expression here. You see now the derivatives do not have the same subindex anymore, so it's not Laplacian anymore. We have subindex I here, we have subindex k here. So in any case, I have a double derivative of the velocity component of v sub I. The double derivative, when I take the double derivative, it doesn't matter the order in which I take the double derivative, so I can swap the positions of these two derivatives here, and I can write it like this. First, the derivative with sub k, and then del sub I. But what is del sub I v sub I? This is the divergence of the velocity. We saw before that the divergence of velocity using void notation is represented by del sub I, v sub I. And we know that for incompressible flow, this should be 0. So this term here is 0. So for every value of k, for k equal 1, so in the direction 1, I have a summation over the index I, so this term will be 0. For k equals 2, this term will be 0. For k equals 3, this term will also be 0. So this term here for incompressible flow will be 0. And this is an important result. We're going to save it here. Therefore, the divergence of the Cauchy stress tensor for Newtonian fluid and incompressible flow is given by this expression here. This big expression just becomes this one. So see, this is a very useful tool. Einstein notation is a very useful tool to work with those equations. Lastly, let's analyze this equation. That was one of the motivations that we had before. How can we represent this equation, or how can we expand this equation with the help of Einstein notation? To do this, let's represent both sides of this equation using Einstein notation. So to the left, we have the double operator, subindex I, and then we have the stress tensor, jk. Then the other term, I use different indices. Well, in this case, because this is a subtraction or addition, doesn't matter, subtraction or addition, I could use the same indices as this one, jk here, and there would be no problem. I the only situation in which I cannot repeat the indices is when I'm performing a dot product or any type of product. Okay, but it doesn't matter. I can use different indices just to be on the safe side, and you're gonna see that it doesn't matter. And the right side, this is the vector f. So we also have 3 directions here. Okay, let's perform the distribution here, this distributive property. So first we have a contraction here between I and j, and then we have another contraction here between I and r. We end up with this expression. So in this side here we have a vector, in this side here we also have a vector, and in the right side we also have a vector, so we are good. We have rank 1 tensors from both left and right sides. Now we have this identity tensor here with sub-indices I and s, and as we saw before, it works just like Kronecker delta. So I can just remove this term and replace s by I or I by s. In this case, I replaced this direction E hat s by E hat I. Now we can see that it doesn't matter the letters that we choose here, because here we have a summation over k, and here we have a summation over I. If we perform the summation over k from 1 to 3, and if we perform the summation of I from 1 to 3, we are going to see that they are the same. So we can simply replace those letters I by k. Well, you can perform this in your mind, or you can take a piece of paper and a pen and perform those summations yourself, and you can see that it doesn't matter. I can replace this. In this case, I can replace these 2 sub-indices from I by k. Now I collect some terms like this, and I have I did the same for the indices on the right side also. So everything is k now. So now if I choose k equal 1, I still have to perform a summation over the subindex I. So for k equal 1, I have fk, f1, f1. I have the derivative of pressure with respect to x1, because k equals 1, right? And now I have the derivative with respect to xi from I going from 1 to 3. So I going from 1 to 3. And the second index of the stress tensor is always 1 because it's k, right? Now k equals 2, k equals 3, and that's it. And that's how we can expand this equation here by using the Einstein notation. And this concludes our talk. So in this talk we have seen a lot of useful, well, at least it's very useful for me, and I'm sure it will be useful for everyone working not just with solid mechanics, but with continuum mechanics in general. And for the next lectures, those concepts will be very useful for us, and I'm going to assume that they are clear for everyone. In case there is any question about this, you can leave in the comments, or you can also drop me an email, and I'll do my best to answer as soon as possible. Okay? So thanks for watching, and see you next time.